So today we're going to be looking at the determinant. Now this is the first part of a two-part sequence where we're going to find the determinant of a matrix in order to find the inverse of a matrix. Now the inverse of a matrix is used to completely cancel out all the terms and reduce it down into the identity matrix, which in essence solves the matrix. So the first step in finding the inverse of a square matrix is we're going to write this down as either the determinant of the matrix, written as DET with parentheses around the matrix title, or what looks like an absolute value brackets of that matrix. Now we realize that when in matrix notation, the absolute value like notation means determinant. So you may see one of each of these depending on the text, depending on the circumstances. So realize in matrix context, in linear algebra, they mean the same thing. So the determinant of a 1-by-1 matrix is just the value. So of a scale value, the determinant of A is A. Enough said. The determinant of a 2-by-2 matrix given A, B, C, D is going to be AD minus BC. And we're going to see how that's created later on. Likewise, the determinant of a 3-by-3 matrix is going to be A times the determinant of this 2-by-2. So realize with this 2-by-2, we'd have to come do the determinant of that minus B times the determinant of this 2-by-2. Again, we'd have to come back and do another 2-by-2 plus C times the determinant of this 2-by-2. And we notice that these values are within the matrix itself. So we're not dealing with other unnecessary points, it's just we're rearranging the matrix into 3 pieces, and boom, we have ourselves the determinant value. So we're not going to get too deep into figuring out how these are worked. We're going to work those in a later problem in this lesson, but let's go ahead and jump into finding the determinant of this. So the determinant of a 2-by-2 we know is going to be, let's say, AD minus BC. And so if we write that out, A times D, it's going to be 3 times 9. So 3 times 9 minus BC, which is going to be 0 times 4. So 0 times 4. 3 times 9 is going to give us 27. Minus 0, it's going to be 27. Pretty straightforward. So we know it's going to be A times D. So I've got these two, and then B times C times those two. Notice the pattern. Let's try number 3. So I know the formula is AD minus BC. We're going to go ahead and inscribe that pattern again. So A times D is going to be a negative 2 times negative 12 minus BC, which is going to be a 0 times a 4. So that's going to be 24 minus 0, or 24. Awesome. So the process of finding these determinants isn't too bad. So what I want you to do is I want you to pause the video, try and find the determinant of 5 and 7. Unpause it when you're done and see all you did. Okay? So let's take a quick look at number 5. We know it's AD minus BC. So what we've got is we have 8 times negative 4 minus 11 times negative 7. So negative 32 plus 77. Let's see, that's going to make it 75, 45. Hopefully you did pretty good there. Number 7 is the identity matrix. So a question that we might ask ourselves is, what would the identity, or what would the determinant of an identity matrix be? Well, we know it's AD minus BC. So now A times D is 1 times 1, minus BC is 0 times 0. So that's 1 minus 0, which is 1. So it's an interesting question to ask is, the determinant of an identity matrix is 1. Identity matrix is the matrix that when multiplied by another matrix produces the same value. 1 when multiplied by any other number gives us the same value. So maybe these two are interrelated. And so as we move to the last one, what we've got right here is we're going to start to see how that formula is made. So now the formula on these is made by a process of what we call cofactoring. We're going to see this here in a moment, but I'm going to give you a clue as to how it's made. We're going to take the first term And we notice that with the first term, I'm going to take a times the determinant of these numbers right here. So it's going to be 1 times the determinant of 6, 18, 9, and 27. So a, if we did that, B, C, D, A, B, C, D, it'd be E, F, G, H, K. Let's see if we got that the same on the formula. So it'd be A times the determinant of the part not included in A. So EFHK, EFHK. Perfect. If we're looking at B and we cover up that central row, it's a little bit too big. Let's try something a little smaller. If I cover up the B column and the B row, it's going to be DFGK. We notice that the B is going to be DFGK. This is what we call cofactoring. So if we look at that process across this entire problem, that's my A. My B is going to eliminate the 6 and the 9 and have a 2, 3, 18, 27. And then if we do the same thing to the last term, if I take the 9 and I cancel out all these, I'm going to have a 2, 6, 3, 9. Oh, yeah, 2, 6, 3, 9. Awesome. And so now with these three right here, I have a 2 by 2, a 2 by 2, and a 2 by 2. I know that to find the determinant of these 2 by 2 matrices, it's just going to be 1 times whatever 6 times 27 is, minus 18 times 9. To do the same right here, to find the determinant of this, it's going to be minus 3 times, this is going to be 2 times 27, minus 18 times 3. And another determinant of the third one is going to be plus 9. It's going to be whatever 2 times 9 is, minus 6 times 3. Awesome. And so with this one right here, let's see, 6 times 27, that's going to be 120, plus 42, that's going to be 162. 90 plus 72, 162. So 1 times 0 is going to be 0. Two times 27, that's going to be 40 plus 14. 40 plus 14, yeah, 54. This is going to be, let's see, 30 plus 24. And this is plus 9 times 18 minus 18. So 0 minus 0 plus 0 is going to give us a determinant of 0. Awesome. So luckily that worked out nice and neat, but we see the process involved in making the determinant involves a process called cofactoring. In fact, that's going to bring us to the second part of the sheet, and we're going to take a closer look at cofactoring. Now, cofactoring is the process of building smaller matrices, of which we saw in the 3 by 3, and these smaller matrices are called minors. Now, the minors are a part of a process called the Laplace expansion. We'll study that in a later section, in a later video. This allows us to find the matrix or the determinant of any matrix that we want. The fun part about creating minors is that if we can spot a matrix with several zeros or several low values, we can create minors that have very simple scalars. What we noticed when we created these right here is we went with the top row, and we went with the top row only. In fact, we actually created the minors right here. When we took the first row, it's 3 times the 9, and when I took the next one, it's going to be 0 times the 4. So 3 times the 9, 0 times the 4. So we were actually cofactoring these 2 by 2s And all we were doing is we were creating this right here. Taking the first one, so A times D minus B times C. And remember, the determinant of a 1 by 1 is that thing, so AD minus BC. We had our A times the minor here, B times the minor here, and C times the minor over here. What we were speaking about previously was what happens if I don't want to use the first row. Can I cofactor using a second or third or fourth row? And the answer is yes. The only thing we have to pay attention to is if we have A minus B plus C, you may have noticed that we changed, for some reason, the second number, and we did not change the third number. The 9 stayed the same on our previous example. And why was that? Well, we keep the first and the third sign if we're using the first row. The second number, we negate it. We take the opposite sign. So if I were using one of these lower rows, I would take the D and change the sign. I would keep the E. I would take the F and change the sign. If I went down to the third row, I would keep the G, change the H, keep the K. So we're going to check out and see if we cofactor using different rows, do we get the same answer? And so let's cofactor this 2 by 2 using row 1. So cofactoring, we said, okay, let's take the 2 and multiply it times the 0. So 2 times the determinant of 0, which is just 2 times 0. And we are going to subtract this one. So 5 times the 4. So 2 minus 0 is going to give me 0, minus 20 is going to give me negative 20. If we cofactor using the second row, this is going to get a little confusing writing on top of this, so I'm going to rewrite the matrix right here. So instead, I'm going to use this row. So I'm going to start out with the 4 and multiply times the 5. But remember, when we start with the second row, I'm going to change the sign of the first one and add the second value. So instead of saying subtract here, I'm going to make the negative out front. So it is going to be a negative 4 times 5. And I'm going to keep the same sign of 0 times 2. So that'll give us a negative 20 plus 0, or negative 20. So we notice that cofactoring using whichever row we want, as long as we abide by the appropriate signs for each term, works out to give us the same determinant. And so let's take a further shot and try that on number 14. On number 14, we're going to cofactor using the first, the second, and the third row. And we should get the same answer for each. So let's practice making sure that no matter which row we pick, as long as we abide by that general matrix sign, we should be good. So if I'm cofactoring using the first row, so let me circle my 2. So with my 2, I'm going to say it's going to be 2 times the minor of 0, negative 2, 1, 0. Next, I'm going to subtract the 6 times the minor it creates of negative 4, negative 2, negative 1, and 0. Lastly, the minor over here, I'm going to keep the sign, but realize this is a negative, so I'm just adding a negative 9. I'm not changing it. Negative 9 creates a minor of those 4 numbers, which is negative 4, 0, negative 1, 1. We're going to see what this evaluates out to. So 2 times the determinant of ADBC. So 0 times 0 minus negative 2 times 1. So this is going to be, let's see, that's going to be 2, so 2 times 2 is 4. ADBC, so negative 4 times 0 minus negative 2 times negative 1. So positive negative. Negative 6 times negative 2 is plus 12. Minus 9 times negative 4 times 1. Minus 0 times negative 1. Negative 4 minus 0 plus 36. So the cofactor using row 1 is going to be 4 plus 12 plus 36. That's going to be 48, 52. So cofactor using row 1 of 52. If cofactor using the second row, zoom out just a bit so we can see more of this. There we go. So using the second row, we're going to do the same thing, except for this time I'm using the 4, the 0, and the negative 2. And so again, if I'm using the 4, I'm looking at the minor it creates, not using the middle row, but 6, negative 9, 1, 0. And again, if I'm using the second row, remember, second row, I start by changing the value. So it's going to be a change, keep, change. So I'm changing this to a positive 4 times the minor it creates of 6, negative 9, 1, 0. I'm going to keep the second one. And now if I cofactor that, I'm going to use the endpoint, so 2, negative 9, negative 1, 0. And I'm going to change the last one. So if I change the negative 2, it will become a positive 2. When I cofactor, I'll have a 2, 6, negative 1, 1 minor. Okay. As we work this down, let's see. This is going to be 4 times 6 times 0 is 6 minus negative 9. So that's 6 plus 9, that's 15. 4 times 15 is going to be 60. We notice that with this, because we picked the second row, 0 times anything, we don't even need to do that step. We can just jump straight to the third minor. So it's going to be 2 times 1 is 2 minus negative 6. 2 plus 6 is 8. $16. 60 plus 16, that's a 76. Pause for a moment. Okay, so what we should have noticed right here is the 6 times the 0 is going to give us a 0. So this is going to be 4 times negative 9, which is going to give us actually a 4 times negative 9, actually 4 times 9, because the negative is still included in there, is going to give us a 36 plus 16, which is going to give us, instead of the 76, is going to give us a 52 again. So apologies on that mistake. Why don't you go ahead and try cofactoring row 3 and see if you get the same answer of 52. Pause the video and pause it when you're done and see how well you did. Okay, now that you've had a shot, let's try this. So we're going to use the bottom of negative 1. And because we're on the third row, I'm going to keep, change, keep. So I keep the negative 1. I change the 1. So this is going to be a negative 1. And then I keep the last one. So 0. When I use the negative 1, I create a minor of 6, negative 9, 0, negative 2. When I use the middle one, I create a minor of 2, negative 9, negative 4, negative 2. And when I cofactor the last one, I create a minor of 2, 6, negative 4, 0. The fun part right here is that we notice that we don't even need to do the third set. I can just completely skip that. It's just a minor of -1 times this and -1 times that. So the minor here is going to be -1. That's going to be -12 minus 0. So 12 minus 1 times -4 minus a positive 36. That's going to give us a -40. So plus 40, 12 plus 40 is again going to be 52. So what we notice is that no matter which row you pick, as long as you follow the cofactoring rules, we get 52 all the way down. So the goal is you can just go ahead and pick the top row, or if you spot that by picking a different row you can skip some steps, skip the steps. Just make sure that you follow the rules of which ones to keep and which ones to change, recognizing those scalar signs. And there you go.